All right, so in this video, we're going to be talking about how to find a basis for the row space and column space of a matrix. Now, the general idea here is that the dimensions of the row space and the column space are the same, and they depend on the number of pivots. And what we're going to do essentially is we're going to row reduce this matrix in order to identify the pivots, and then we are going to select vectors from our matrix depending on the locations of those pivots. So let's start by row reducing in order to find the pivots. So if I row reduce, I am going to get the following matrix. All right, so if I row reduce, I get this and that, and this becomes a 0, and this becomes a pivot, and this becomes a 0, and that becomes a 0, and this becomes a 1, and this becomes -14, and this becomes 5, and this becomes 27, and this becomes 25/4, and negative, oh, that's bad. -15/4, and this becomes -57 divided by 4. All right, so given that we have this as our reduced matrix, we have 3 pivots in the first 3 columns. Now, doing row operations on row vectors does not change the span of the vectors. So to obtain a basis for the row space, you can use the reduced vectors from the reduced matrix or the vectors where the pivots occur from the original matrix. So row space, row A, would be the span of, so there's 3 pivots, so there'll be 3 vectors. And we can use 1, 0, 0, -14, 25/4, 0, 1, 0, 5, -15/4. Oops. Back up. Oh, there we go. 0, 1, 0, 5, -15/4. And then 0, 0, 1, 27, and -57/4. So that's fine. Or you can do row A as the span of vectors from the original matrix. Our original matrix had entries of 1, 3, 0, 1, -5. And 2, -1, 1, -6 and 2, and 4, -5, 3, 0, and 1. Assuming I didn't make any typos, basically this just looks like the transpose of the original matrix of entries. Now, for the row space, you have these two options, but for the column space, you can't do that. For the column space, performing row operations on column vectors changes the span of those vectors. And so it doesn't change the dimension, but it does change the specific kinds of vectors you can solve for. So for the column space, you must go back to the original matrix to get the basis for the column space. So column A is going to be the span of, again, also 3 vectors, but now the columns are only 3 dimensions long. So 1, 2, 4, and 3, -1, -5, and 0, 1, 3. Now, this is especially important if the column space does not span all of Rm. So if the column space does not have a pivot in every row, then this is, let's just say, especially important. Now, in the case where you do have a pivot in every row, as in this case, what you end up with is a set of basis vectors that spans, in this case, all of R3. And so if you were to pick the identity matrix, you would also have a basis for R3. And so you'll sometimes see this with technology, like if you're using MATLAB, for example, and you ask for a basis for the column space. If the column space is all of Rm, then what it's just going to do is just going to give you the standard basis vectors. It's going to give you the identity matrix. It's not going to give you the vectors from the matrix itself. However, again, if you don't have a pivot in every row, then you're going to need specific vectors, and then you will get different results. You'll actually have to use the columns from the original matrix. So you can only use the reduced form for the identity if it spans all of Rm. Now remember, this is a 3 by 5 matrix, so that means this is M by N. And so this is a Rm span. And so this is our R3 space that we're trying to find vectors that we can get to in R3. And so if we can get to every vector in R3, then we can use any basis we want as long as it's a basis for all of R3. And that's essentially what we have in this particular example. But again, that is not the standard. And again, you can't do that if you don't have a pivot in every row. All right, so in another video, we're going to look at the dimensions of the column space and the row space and the codomain and the range. I will, of course, just mention before we leave here that when you have a row-reduced matrix like this, you obtain the null space as a solution to the homogeneous system from the reduced matrix, and you do need to reduce it all the way to reduced echelon form in order to get to that null space. When you're doing the row and the column space, you only need to go far enough to identify the pivots. So echelon form would be fine. But if you're going to continue on to find the null space, got to keep going.